When doing tissue image analysis, after training your model, how do you check if this model is good enough? What are the metrics that you should use for different computer vision tasks in tissue image analysis? If you're asking yourself this question, this video is for you. Hi, I'm Alexandra Zhurev, and I'm here to help you do better digital pathology and help you check if your deep learning model for pathology is actually good enough. This is part of a webinar I gave for the C.L. Davis Foundation. The webinar was part of a one-day paid event, and I was honored to be a speaker at this event. I divided it into smaller pieces to address every topic in the webinar separately, but if you want to watch the full thing, you will find the link below in the description, and also there's going to be a playlist that you can binge watch if you feel like it. So what are the different metrics that you can use to check if your deep learning model is good enough? Is accuracy enough? Or maybe sensitivity and specificity? Or maybe you should use the F1 score? Which one is it? Do I need to use all of them or just pick one? There's definitely no one size fits all. So let's dive into all the different metrics and let's learn which metric is optimal for which type of computer vision task for which type of tissue image analysis problem.
Performance metrics. So why do I say it's tough? I have learned this so many times for different tests, and probably you already have for the boards, for CleanPath, because these performance metrics are not really different than performance metrics for other tests. And every time I have to relearn it. So I hope that this time with some mnemonics, at least some of this is gonna stay. So we have many different metrics, and don't worry, we're not going to talk about all of them. We're going to just cover some. And let's start with a few key points. First, one metric is never enough. Those tasks are complex, and for none of any tests ever, one metric is enough. You at least have two and more. And the mathematicians would give you a lot of potential evaluation metrics. I am not a mathematician, so I will only talk about a few that I think are crucial for us to understand so that we can compare models to each other when we are developing them. We can look through literature and see, okay, is it actually good performance or it's not really good performance? But anyway, important thing, always more than one metric. Accuracy, which is a very omnipresent performance metric, is often not enough. And we're going to talk about it, why it's not enough. And some metrics are specific to a certain computer vision tasks. Some are not, some are across the board, but some are more specific. We're going to talk about them. So feel free to take a screenshot of this. And no worries, we are only going to be talking about the upper ones. So different metrics for different computer vision tasks. For classification, we can use accuracy, sensitivity, and specificity. Receiver operator characteristics curve, area under curve. These are combinations. So the one below the square are some kind of combination of the upper metrics. We're only going to cover the upper metrics. For object detection, it's going to be precision and recall, which is the same as sensitivity. Intersection over union, which is the same as for instance segmentation on the right side of the table. And for semantic segmentation, it's going to be precision, recall, and F1 score. That's important, for example, that semantic segmentation and instance segmentation have this metric that is different. And it's good to know that because then you can evaluate your model or discuss this better, even if you're probably not the person performing the calculations. It's either the software doing this for you or a computer scientist working with you. But equipped with that knowledge, you are a partner in the discussion. Let's start with the basic concept in those metrics. Confusion matrix. Confusion matrix is a matrix, a graph. It's not really a metric. It is a visual representation of what's happening in our classification. So we have up here true class. The green is the true class. And we have on the left the predicted class. And we can, if our true class is positive and we predict it as positive, then it's true positive. Excuse me. So if we're looking for our cartilage and our mask is telling us, yes, this is cartilage, it's a true positive. But when it shows flax bone as cartilage, it is then a false positive. False positive meaning the true class is negative, bone, but our classifier predicted it's cartilage. No, it's false positive. And then again, if true class is cartilage, but we predict it as bone, it's false negative. And then if it's non-cartilage, for example, bone, and we predict it as non-cartilage, true negative. So the green ones are the correct ones and the red ones are the non-correct ones. And the metrics are built around those true positives, false negatives, and true negatives. And basically, in medicine, if we want to approach it a little bit like systematically, we have two types of tests. We have diagnostic tests, and we have, for example, any diagnosis on glass is a diagnostic test. And here, both false positives and false negatives are a big deal, because false positive is someone with no cancer that gets treatment. This is no good. Cancer treatment is a big deal, right? Chemotherapy, and this is not something harmless for a healthy person. And also, if we have a false negative, when somebody has cancer and we say, no, you're okay, then the cancer keeps growing and we send home a sick person and we're responsible for this person not being treated. And a screening test. And for example, screening test, if you are a woman and have been pregnant, you probably had to drink this. This is the pregnancy glucose test. They screen you for gestational diabetes. So in this case, a false negative would be a big deal because we want to send healthy people home. The true negatives are healthy people. If we send a false negative, meaning a sick person home, we're sending somebody with diabetes home. We don't want that. Whereas a false positive in this case, somebody who the test says, oh, you might have diabetes, but they don't. It's not a big deal because we then have another test that is a diagnostic test and is supposed to later say, okay, was the screening test correct or not? So here we're going to optimize for different metrics. And it is super simplistic and there are different applications, but to understand the metrics, it helps to ask yourself the question, am I working on a diagnostic test or am I working on a screening test? And then you will know what's more important for you. So for image analysis, pathologists want to ask themselves a couple of questions and want to have a certain answers to those questions when the algorithm is supposed to be useful. So for example, one thing, do the markups correspond to what I see in the slide? In our example, do my pink and blue markups correspond to cartilage and non-cartilage? Yes, then green light. Then am I going to do harm if the algorithm doesn't perform well? I don't want to do harm. If that was a diagnostic algorithm for cancer, I don't want to do harm by saying you have cancer if you don't have it, nor you don't have it if you have it. So there is optimization, but basically I don't want to do harm by using image analysis. And another thing is I have to work more if the algorithm doesn't perform well. So let's say the screening algorithm would not perform well. So in general, like from life death perspective, not a big deal because you send more people for an additional test to rule out or rule in. But if there are too many of those false positives, then you have to do more work than you would have to do otherwise. So again, this is no magic tool. You always ask yourself, okay, is it worth using this tool? What is the barrier to developing it, and also what can the damages be if it doesn't perform well? So that guides the metrics as well. And there are metrics for classification. We said accuracy, sensitivity, and specificity. So the classic ones for other tests as well. Accuracy is true negatives and true positives over everything. So when we look here, true negatives and true positives, so the real ones over everything. So obviously, we want to have here as close to 0 and here as close to 0 to have good accuracy. The problem is that we already said that many classes are underrepresented. So we have an underrepresented class in a sea of something that is very abundant. Let's say, not Chi-6, yeah, let's say Chi-67, few Chi-67 positive cells in a sea of negative cells. So what happens if, with accuracy, if we have a classifier that says everything is negative in such an underrepresented class? We have 1,000 cells in total, 40 are Chi-67 positive and 960 are Chi-67 negative. So when we say all cells are always negative, we have 0 true positives and 960 true negatives and 40 false negatives, because we don't have, the classifier says it's all negative. Everything is negative. And the accuracy is beautiful because we have true negatives and true positives. It's divided by everything. It's 96% accuracy. That's a fantastic model, right? Obviously wrong. That's why accuracy is not a good metric alone, especially for problems where we have a class that is underrepresented, which is most of the problems that we have in pathology. So we use it, but in combination with other metrics. And the metrics that we use is, for example, sensitivity, which is true positives, the real ones here, over true positives and false negatives. So if we have our numbers, we have 30 true positives and in total 30 plus 10 true positives and false negatives, what is our sensitivity? It's 35%. We can, depending on what we want to achieve with our algorithm, we either want to have it higher or this is okay for us, but this is one of the metrics. And sensitivity, what influences our sensitivity is those false negatives. False negative is somebody sick that we send home. We don't want to send a sick person home, but we don't mind rechecking a healthy person. So like for the diabetes test. So this metric is often screening tests are optimized for this metric. So if we're developing a screening test, we're going to be optimizing for sensitivity. Then specificity, true negatives. So here before we had true positives. So we were calculating this and this was skewing our equation, false negatives. Whereas in specificity, it's the other way around. We have true negatives at the top and true negatives and false positives at the bottom. So here are our numbers, and specificity is better for our numbers, right? Because we're talking about the negatives, and here we have bigger numbers. It's a good specificity. So good for diagnostic test. So here false positives are our problem. If we have too many false positives, our specificity is going to go down. And those false positives are false alarm. So we want to avoid false alarm. First of all, we want to avoid it if we have a screening test. We don't want too many false alarms because every false alarm makes us work more or makes us pay, or the healthcare system pay for additional tests. So there is a certain number we can afford, but not too much. Yeah, so false positives, not too many for specificity. And this maybe will help us remember what to optimize for. This little sentence to remember: snout to rule out, spin to rule in. Snout, sensitivity for a screening test. This is what we would optimize for. And spin, specificity for a diagnostic test. Obviously, diagnostic test cannot have there cannot be any test that has 100% and the other 0. That doesn't make sense. But depending on the intended use, we optimize for a different metric. Snout to rule out, screening, we rule out people who are healthy. Spin to rule in, we rule in people who have the disease, who are sick. And this obviously applies to our image analysis tasks as well. Metrics for object detection and instance segmentation. And this is nice because we have the same metrics. And that's good. Why do we have the same metrics? Because here the same things are happening, just with a different level of detail. So instance segmentation, this delineation of particular objects is going to be more detailed. And here we have bounding boxes. I see something in the chat. Okay, no, all good. So yeah, at least we have the same metrics for two problems. That is good. It saves us something. So we have precision, we have recall, which is sensitivity. And I don't know, maybe in English it makes sense. English is not my first language. I struggled with remembering why recall is sensitivity. Now I have a little trick to remember. If I want to call someone about a sensitive subject on a sensitive issue, then I have this call part, and sensitivity, it's the same. Recall is sensitivity. For all non-native speakers, maybe it's gonna help. Yeah. So, moving on. We want to have a little bit of time for questions and answers as well. Precision is also known as positive predictive value. I hate that those metrics have 3 names. If you go to the Wikipedia page, there's 5 other names for this. I only pick those that we as pathologists or like medical professionals are familiar with. But if you talk to a mathematician, it has 7 other different names. Anyway, positive predictive value is percent of correct positive predictions among all positive predictions. And this probably doesn't tell you anything unless we see our matrix. So we have true positives, our cartilage, over true positive and false positives. So this metric that is going to cause us trouble, the number of errors that is going to cause us trouble are going to be the false positives. False negatives are not part of the equation. And this is also a little trick that I have seen in those metrics. Okay, you look at the equation and what's causing trouble and what is not. And then if this thing that is causing trouble is the problem, you optimize for this metric and the rest is not so relevant. Hopefully this helps as well. So our numbers, again, here our precision is not so high. We had accuracy of 96. Then the next metric was specificity, specificity. No, I'm gonna go back. I don't want to confuse you. Yeah. So we had sensitivity, so accuracy of 96, even though everything was negative. Then we have sensitivity 75. Okay, because our specificity is 0.96 again. And what about our accuracy here? It's only 0.5, so it's not so beautiful. But that's what it is. And sensitivity recall we already had. Our sensitivity is 75, not too bad. So yeah, here for object detection and instance segmentation, the pair is precision and recall. For the classification, the pair is sensitivity specificity. And again, for sensitivity recall, the false negatives. So a sick person sent home, false negative. We don't want to do that. And it's good for screening tests. Something that is specific to those instance segmentation and object detection is intersection over union. And you might not have heard the name, but I think when you see it, this is going to be the most intuitive of the metrics, even though the other ones, I come across them all the time. Intersection over union is telling us how the ground truth bounding box or the ground truth annotation in terms of instance segmentation is corresponding to the predicted bounding box. So here, the green one is the ground truth box where the stop sign is. The predicted one is a little bit shifted. It doesn't look too bad to me either. They're not 100%. And to measure how good that is, we have intersection over union, which is area of the overlap. So it's pretty big area over the area of union of those boxes. So when we use this, we have to ask ourselves, okay, how much of this is still going to be considered correct? If it's totally just touching with 1 pixel, do we still say it's correct, or is it not enough for us? So you will see that in your images, in your markups. And on the lower picture, we can see if it's 0.4, that's poor, even though there is enough overlap, but that's poor prediction. 0.7 is okay. I think that's the stop sign would be 0.7, and 0.9 is fantastic. If we have intersection over union, it's 0.9. It's as if two different people, probably when they draw the same thing, they don't have the same overlap. So that's perfect. And metrics for semantic segmentation, it's precision, recall, and F1 score. We already had precision and recall. So here it's not intersection over union because we don't have particular objects. We just have region. So this is region of giraffes. So the thing that differentiates this one is the F1 score. And F1 score, I do not have a nice visualization for you because this is a more complex mathematical operation than what we had before. And F1 score is a balance between precision and recall. So it's 2 divided by 1 over recall plus 1 over precision, or you can also, it's so-called harmonic mean of precision and recall. In the upper one, you would have recall times precision, and in the lower, recall plus precision. Anyway, that's beyond my current mathematical capabilities. The take-home message, and I hope you have better mathematical capabilities than me. I use calculator for everything at the moment and don't trust myself even with simple additions. And I'm okay with that. But what we have to know here, there is this F1 score. It's a balance between precision and recall, and we use it instead of accuracy for uneven class distribution. So when we have this underrepresented class, F1 is gonna be our metric and not accuracy. And that's it from my side.
You stay till the end, you are serious about this, because this is not an easy thing. If this was helpful, give this video a thumbs up and put in comment which thing was the most useful for you today. And I talk to you in the next episode.